A warm welcome to this session. In this session, we will discuss about some definitions regarding Weingarten maps. Last class, we have discussed about the definition of derivative of a function with respect to a vector. So today, the definition what we will discuss here is definition definition. Let S be an n surface. Let capital S be an n surface in Rn plus 1 and f from S to R be a smooth function. Be a smooth function. The derivative of f, the derivative of f with respect to v, with respect to the vector v, tangent to s, tangent to s is defined as, is defined by del v of f is equal to f composition alpha dash of t naught, where alpha from I to S be any parameterized curve, be any parameterized curve, any parameterized curve in S with alpha dot of t naught equal to v, alpha dot of t naught equal to v. So as we have seen the derivative of a function with respect to a vector, here also the definition is going to be the same. One specialty over here is that v is tangent to s. So the entire what we found the derivative should be tangent to s. So note that f from s to r is a smooth means that f is the restriction of f is the restriction of a smooth function f tilde defined on an open set containing S, the remark 1. Remark 1. Del Vf is independent of the choice of alpha in S, independent of the choice of alpha in S with alpha dot t naught is equal to velocity v, and passing through p. This also we have seen there, but this is what we are discussing here is this is tangent to. That's right. So del Vf, so we can take this del Vf as uh, f tilde. Since we have already this stated that f is said to be smooth whenever this f is going to be a restriction of a smooth function f tilde defined on an open set. So this f tilde composition of alpha of T naught. And using chain rule, we can reinterpret this as del f tilde of alpha of T naught dot alpha dot T naught. And this is nothing but del of f tilde of P dot V, where we haven't specified what is f tilde. So let me specify it here, where f tilde from U to R is any smooth function, defined on an open set, defined on an open set U containing S, U containing S, whose restriction, whose restriction to S is F. See here the problem is that it's given that f is going to be a continuous function and f is going to be smooth. But smoothness we always refer to open sets. So here f is defined on a surface. So we should go for its extension to an open set. So first of all we are taking an open set U and we will restrict that f to our surface S. So f tilde restricted to S is going to be our smooth function f. So remark 2, the function which maps v to del v of f is a linear map, is a linear map from SP to R. These two we have discussed in last class. That means in the general class we have discussed about del Vf and this map. So in particular when this V is going to be a tangent, let us see it, del V plus W of F. By definition it is going to be del F tilde of P dot V plus W, and this is equal to del F tilde of P dot V plus, we know that dot product is the distributive over vector addition. So I am using that rule over here and we will get del f tilde of P dot W. And this can be written as, by definition, this quantity will reduce as del V of f tilde. And this quantity will reduce as del V of, del W of f tilde. Also, we can easily check that del CV of F, that's equal to del F tilde of P dot CV, and this can be written as C into del F tilde of P dot v, and this is equal to c into del vf for every v comma w belongs to s. So these arguments are going to be similar that we discussed in our previous class. So I'm not going in detail of that. Next definition: the derivative of a smooth vector field. The derivative of a smooth vector field x on an open set U, on an open set U in Rn plus 1, in Rn plus 1 with respect to the vector v, with respect to the vector v belongs to Rpn plus 1, comma p belongs to U, is defined by del v of x is equal to del vx equal to x composition alpha dash of t naught, x composition alpha dot of t naught, where alpha from I to u is any parameterized curve, any parameterized curve, in u such that alpha dot of t naught is equal to v. So let us see what is this. It says that the derivative of a smooth vector field x on an open set U in Rn plus 1 with respect to the vector v belongs to Rpn plus 1. Previously we have discussed about derivative of a function with respect to a vector. Here what we are going to see is derivative of a vector field with respect to another vector. So del v of x, that's by definition, is defined as x dot alpha derivative at the point t naught, and similarly alpha is from I to u is any parameterized curve in u such that alpha dot t naught is equal to v. As a note, for x, for this x, a smooth vector field, a smooth vector field, a smooth vector field on an n surface, on an n surface S in Rn plus 1, in Rn plus 1, and V a vector tangent to S, at P belongs to S, the derivative del Vx is defined by the same formula where alpha is required to be, alpha is required to be a parameterized curve a parameterized curve in S with alpha dot T naught is equal to V. Alpha dot T naught is equal to V. In both situations, del Vx belongs to Rp n plus 1 and that uh, del Vx is equal to alpha of T naught, comma, x1 composition alpha dash of T naught, etc. Last quantity should be xn plus 1 composition alpha dash of T naught. So this is your del V of x. So this can also be written as this is equal to p comma alpha of T naught is p. This can be written as del V of x1 etc. Del V of xn plus 1, where the x's are components of x, where x equal to p comma x1 x2 etc. xn. That is going to be the components. In particular, the value of del Vx does not depend on the choice of alpha. On the choice of alpha. This too we can prove similarly. So here is the question. Show that differentiation of a vector field has the following properties. The following properties. First one, del V of x plus 1 is equal to del V of x plus del V of y. So first property. Second property is del V of fx is equal to del V of f into x of p plus f of p into del Vx. And third one is del V of x dot y is equal to del V of x dot y of p plus x of p dot del Vy. For all smooth vector fields, x and y on U. on U or on S or on S, and all smooth functions and all smooth functions f from U to R or f from S to R. So we want to prove these three properties over here. So the first property what we want to prove is del v of x plus y is equal to del v x plus del vy. So solution to prove del v of x plus y is equal to del v of x plus del v of y. No need of writing bracket. So take your x as alpha of t naught, comma x1 t naught, x2 t naught, extra xn plus 1 t naught, xn plus 1, and y is equal to alpha of t naught, comma y1 t naught, comma y2 t naught, comma extra yn plus 1 t naught. Now x plus y is equal to x plus y is equal to alpha of t naught, comma x1 plus y1, right? x1 plus y1 t naught, or x1 t naught plus y1 t naught plus extra xn plus 1 t naught plus yn plus 1 t naught. So this is the function. Thus del v of x plus y, del v of x plus y is equal to alpha of t naught as such. Next what is coming is x1 plus y1 composition with alpha dash of t naught plus etc. Last term should be xn plus 1 plus yn plus 1. This composition with alpha dash of t naught. So this entire thing. Now this can be written as del v of x plus y is equal to alpha of t naught, comma x1 composition alpha dash of t naught plus y1 composition alpha dash of t naught, comma etc. Last term should be xn plus 1 composition alpha dash of t naught plus yn plus 1 composition alpha dash of t naught. So I should use. Now this is nothing but, you can write this as alpha of t naught, comma x1 composition alpha dash of t naught, right? I'm collecting only x1 x2, so x2 composition alpha dash of t naught, comma etc. Last term should be xn plus 1 composition alpha dash of t naught plus you will get next value as alpha of t naught comma y1 composition alpha dash of t naught comma y2 composition alpha dash of t naught extra yn plus 1 composition alpha dash of t naught. So this is nothing but del v of x, it is first one, right, plus del v of y. So we have proved this result. Del v of x plus y is equal to del v of x plus del v of y. Next we want to prove del v of fx and del v of x dot y. So these two I'm leaving for you to work. So complete it. I will give you the clue. As in the same way, you can continue by taking x to be with its component function x1, x2, x3, etc., xn plus 1, and y to be again y1, y2, y3, etc., yn plus 1. And this f, you keep f itself and use your derivative rules and all. You will easily get these two. Okay. So I'm winding up today's session over here. Thank you for your patient listening. Thank you.